So this is the example that I gave at the end of last lecture. So this continuation from our discussion about work done. So in our previous example, the work done in moving a charge, 1 millicoulombs charge in a uniform electric field of 150 watts per meter is calculated to be 4.5 times 10 to the minus 5 joules. And then we move on to look at potential difference. So what's the potential difference between endpoints of the path of this example here? Okay, so simple calculations. The potential difference is equals to the work done divided by the charge, and that worked out to be minus 0.045 volt. Okay, so this is just a recap a little bit. So potential difference from the last lecture, V equals to work done divided by Q, and that will be equals to minus the integral of E dl. And then the work done previously we look at is equals to minus Q integral E dot dl. Okay, so that's potential difference. So we're now going to look at, in today's lecture, electric potential. Again, we use a symbol phi here. Okay, suppose we have a point charge Q at the origins and another point charge, a small letter q, at a vector positions r. And we take this in a free space at the moment. So if it's in a dielectric materials, we simply account for that with an additional factor epsilon r. Okay, so we treat this in free space. So it is free space, which means that epsilon r is equals to 1. And that if needed, if we want to look at this same scenario in a dielectric materials, we simply account for that with epsilon r. Okay, so what is the we're going to look at what is electric potential. So let's see how much work we have to do to take the charge Q along a distance away. Okay, so let's say this is my charge at the origin. If I want to move a charge, small letter q, here from some distance r to a very far away, somewhere in infinity. Okay, so we're going to take this small letter q charge from some distance r from the origin where my plus q is sitting, from that point all the way to infinity. How much work is done? Okay, so for simple calculation, we're going to move along the electric field. So point charge, electric field pointing radially away from the point charge. So we're going to move this small letter q charge along my electric field to infinity. Okay, so we're not going to do this. Okay, this is just going to make things very difficult to calculate. So we're going to move it along the electric field so that our d dot dl simply equals to d times dl. Okay, so if you move along the electric field, the dot product of the vector, they are aligned. So the dot product is simply the multiplications of the magnitudes. So that makes calculation simple. If we move in these directions, then the dot product become very complicated, very difficult to solve. We're not going to do that. So we choose a simple scenario to solve. Move our Q in the direction of the electric field. Okay, so our equation 2, work done, dW equals to minus Q integral of E dl. Okay, because we move our charge Q along the electric field. Okay, so it is just the multiplications of the two magnitudes rather than doing a dot products of two vector. And we're going to move from R to infinity. So our work done, W, will be equals to minus Q integral from R to infinity E dl, or dr in this case, because it's in the radial directions. And we know our electric field, our point charge electric field, that will be equals to Q over 4 pi epsilon naught R squared, and then dr. So integrate 1 over R squared against dr, that will be equals to 1 over R, or minus 1 over R. Okay, so the integral of this will be minus Q over 4 pi epsilon naught R. So integral of 1 over R will give you minus 1 over R. Okay, so so our Q over 4 pi epsilon naught, that is simply a constant, so that doesn't change in our integral. So it's just 1 over R squared, it becomes minus 1 over R. Limits is infinity. Okay, so limits is infinity, so 1 over infinity, that will be 0. Okay, and then 1 over R. So this come out to be, so this bracket here, that will be minus 0 minus this whole thing here, Q over 4 pi epsilon naught, and then R will be R. Okay, minus. Okay, so because we have a minus sign here, so it's minus Q over 4 pi epsilon naught R. And this become positive, we got a minus sign here, so therefore we have minus small letter q, and then big letter Q, which is the Q of the charge in the origins, over 4 pi epsilon naught R. And that will be the work done to move the charge from R to infinity. Okay, so we're moving, so we have a charge plus Q, and then we're moving a small charge Q here from R to infinity. And that's the amount of work done in order to achieve that in the presence of that electric field created by the plus Q. Okay, if we reverse this process, meaning that if we're going to bring this charge from infinity to this point Q, this point where Q is, which is R distance from plus Q, then we're just simply going to reverse the limits from infinity to R. And therefore, if you go through the process, this just becomes positive instead of negative. Okay, so the work done to move from infinity to R, that will be equals to Q, small letter q times big letter Q over 4 pi epsilon naught R. Okay, so that's the work done. And why we calculate the work done? Because we want to calculate the potential difference between the point where R is, or where the small q is, which is R distance from the origins, compared to infinity. So potential difference is the work done divided by Q, and therefore we work out that the potential difference for a charge, okay, between this point and infinity. So the potential difference between this point to infinity, that will be equal to Q over 4 pi epsilon naught R. So you can think of this, that the potential at infinity is actually 0. So that is our reference. Just like in your circuit, that will be your ground point. Okay, so in your electric circuits, you always measure the potential with respect to ground. So here in this case here, our ground is at infinity. And then the potential at a particular point, which is a distance r, that will be that potential at r minus the potential at infinity. And for our point charge, that will be equal to Q over 4 pi epsilon naught R. Okay, so we set the potential at infinity equals to 0, and we define the electric potential at some distance r from a point charge Q as Q over 4 pi epsilon naught R. Okay, so this is our potential at a distance r from the source, and our source is, this is our source, plus Q. Okay, so if you look at this definition, so our potential is equals to Q over 4 pi epsilon naught R, and that is equals to W over Q. So another way to think about potential is the work done in moving a charge of 1 coulombs from infinity to that point. Okay, so if my Q here is 1, then this will be the work done, W, to move that 1 coulomb charge from infinity to the point R. And then it said that it's not very rigorous definitions, because as I mentioned very early on, 1 coulomb is a rather large charge. Okay, so it's almost impossible to move a 1 coulomb charge from infinity to a point because it's such a big charge. But it's a useful definition to give you an idea what is the electric potential, that is W over Q. If Q equals to 1 coulombs, then my potential will be equals to the work done. And you can see that the potential, the electric potential, just like your potential difference or voltage, is a scalar. It doesn't depend on directions. Okay, so electric potential is a scalar value or scalar quantity, also have a unit volt, just like your potential difference. So because it's scalar, so you can sum up potential just like a number. Okay, you don't have to consider about the direction. So the potential can be a sum of many different contributions of different potential. So for example, I have, in this example, I have 1 point charge. So I calculate the potential here. But if I have another point charge, then the potential here due to 2 different point charge, you can work out the potential independently and then sum it up, okay, doing a superposition. And because it is scalar, you don't have to consider about directions. Unlike your electric field is a vector, you need to know the direction of the vector field. So if it's a electric field, you know that this is my electric field due to my charge Q1, and this is the electric field due to charge Q2. So to sum the electric field is a vector summation, so the direction of the field important. But the potential is a scalar, so all you need to calculate is this value here, okay, Q over 4 pi epsilon naught R due to charge 1, and then Q over 4 pi epsilon naught due to charge 2, and then you just sum the two potential. Okay, so that's make it very useful and easier to calculate compared to a vector electric field. So to find the potential difference between 2 points, if I have a point A and B, then I can work out the potential at point B and then the potential at point A and take the difference between the two potential. Okay, very similar to your circuits. I mean, if you want to work out, if I have like your circuits, to work out the potential drop over this resistance, you can work out what is the potential at this point here and what is the potential at this point here. We call it V1, V2, and this potential is just the difference between that two potential. Okay, so similar in here, the potential difference is the difference of the electric potential of the 2 points, point A and point B. And then you can work out the work done to move a charge between that 2 points by simply multiplying that potential difference with the charge that you want to move. And that will be equals to Q phi B minus phi A. Okay, so that is potential and the usefulness of it. You can calculate potential difference by just working out the individual potential at a particular point and then do the difference between the 2 points, the potential between the 2 points. Okay, so that's the theory and explanations. So here's an example of how you can use the equations that shown to work out work done and potential difference between 2 points. Okay, in this example, we have a charge Q plus Q sit at a point A, and then a charge minus Q sit at a point B, and the two charge is separated by a distance D. And then we have another 2 point D and C, also a distance D, and the distance D is 10 centimeter. Okay, so plus Q is 10 nanocoulombs, minus Q is minus 10 nanocoulombs. Okay, so you asked to find the potential difference between point D and point C. So you want to find the potential difference between point D and point C. So for example, what is VDC? Okay, between these 2 points. Okay, so what you want to do is to work out what is my electric potential at the point D and what is my electric potential at point C. And then my VDC will be VD minus phi D minus phi C. Okay, to find the potential at D, you can use the equations Q over 4 pi epsilon naught R. R is the distance from the source. Okay, so there are two sources here. So to find D, at point D, we have one due to A, which is a plus, and one due to B minus Q. And then it will be the sum of the two. Okay, so you can simply put it as D equals to Okay, the potential due to plus Q and the potential due to minus Q. And that's the electric potential equation. Phi equals Q over 4 pi epsilon naught R. Okay, so for plus Q, there will be plus Q over 4 pi epsilon naught, and R is 10 centimeter. And then for the phi minus Q, the charge will be minus Q over 4 pi epsilon naught, and the R, this is the distance between them. Okay, so that will be square root 2 of 10 centimeter. Okay, and then the potential at D will be the sum of these two. And then you can do the same for C as well. For C, again, you have due to charge plus Q and due to charge minus Q. And then the potential difference with VDC will be the difference between phi D and phi C. Any questions? Anyone doesn't understand how to solve this? And then if you can find VDC, then the next part is to find how much work is done moving a charge of 1 nanocoulombs between C and D. Okay, that's simply multiplying VDC with 1 nanocoulombs, assuming the charge is sitting in free space. Okay, so this is the solutions. Okay, it's better to show it as plus and then minus Q on the top, okay, because it's the sum of two different potential, so it's not a difference of two different potential, but there is the same thing. It's just that in terms of presentation, this is more representative. Okay, everyone got that? Anyone not understand? So this is one way of solving this problem, and this is the simplest or the simpler way of solving. I wouldn't say the simplest. This is the simpler way of solving this problem. Okay, so another way you can solve this is that we know potential difference is the integral of minus integral of E dot dl. You can actually solve it using this equation 3, but it's very difficult. Okay, I wouldn't even try to do it because it's very complicated, as I said, because the electric field is a vector. Okay, so we have two charges. So you need to find the electric field along this path, and it is a vector. Okay, and this electric field is not in the same direction of your integral path, because if you look at it, I have one electric field that is pointing in this direction, and then I have one electric field pointing in this direction. Okay, so you need to work out that electric field, and then you want to find out the resolved electric field in this direction to do the integral. And then that electric field changes as you go from D to C. Okay, because when you move from D to C, the distance from A along that path changes, and the distance from B along that path changes as well. So this is a very difficult sum to solve. But you can see that we have solved the same thing. We work out the potential difference quite easily using the electric potential roots, because they are all scalar, and you just need to find out the electric potential, and you can just sum them up using superpositions. Okay, so there is electric potential and how you can use it to find the work done, and also potential difference between 2 points if you have more than one source of electric field. Any question on that? Everyone good? Know how to solve this? If I give you a different scenario with the point charge at different locations, you can work out the electric field. You can work out the potential difference. Yep. So instead of a square like that, maybe I put another charge here. And ask you to work out the same VDC. I'm sure you know how to do that, right? So you just work out the additional electric potential due to the 2 plus charge, if you want to do that. Okay, so if I add another charge here, you just need to know the distance x to work out the potential at phi d, and you need to know this distance to work out the potential for phi c. Okay, and then the potential difference is just like what you have done just now. Okay, so these are the things that you need to know how to calculate. Okay, moving on. Relationship between the electric field and the potential. So we work out the electric potential, and now we want to find out the relationship between the electric field and that potential. So consider a uniform electric field of magnitude E parallel to the x-axis. Using equation 4, I have equation 4 down here. V equals to work done over the charge is equals to minus integral E dl. And just now we find that the potential difference is equals to the electric potential at point B minus the electric potential at point A. And that will be equals to minus integral of moving from a distance xa to xb E dx. If I do this integral, that will be equals to minus E, the difference between xb minus xa. Okay, so we work out at an equations that VBA equals to phi B minus phi A equals to minus E. Okay, so from this equation, we can work out what is the electric field. Okay, so the electric field is simply equals to minus of phi B minus phi A over xB minus xa. Okay, that is some form of a gradient. Okay, so remember when you learn linear equations, gradient m equals to y2 minus y1 over x2 minus x1. Okay, so that is your linear equations gradient. Here we have phi b minus phi a over xb over xa, negative. So the electric field is a negative gradient of something. Okay, so it's the negative gradient of the electric potential. So the electric field is equals to minus potential difference VBA over XB over minus XA, and that equals to the electric potential at B minus the electric potential at A divided by XB minus XA. So that is a negative potential gradient. Okay, so the electric field is a negative of the potential gradients. And the unit itself of the electric field, the unit of electric field is V over M. Okay, V is the potential difference units, volts, M is the distance. Okay, so that is electric field. Electric field is a negative gradient of the potential. Example, if I have an electric potential phi x for a uniform electric field of magnitudes E, electric field magnitudes of E equals to 2 watts per meter, pointing along the positive x-axis. Okay, so this is my scenario. I got electric field uniform pointing in the x-axis. At x equals to 0, we have the potential equals to 8 volts. So sketch the surface on which E is constant. Okay, so first you ask to sketch the potential change as a function of x, and then next you ask to sketch the surface on which the potential is a constant. Okay, so this is how the potential will look like. Okay, come back to that graph. So this is how, so we said that the electric field equals to the negative potential or negative gradient of the potential. So that will be minus phi x minus of minus phi 2 minus phi 1 over x2 minus x1. Okay, so that is our electric field equations, and we are given that one of them, which is phi 1 at phi of 0, and that is equals to 8 watt. Okay, so this is where x equals to 0, and that is the information we are given. So phi 1 equals to 8 watts, x1 equals to 0, and therefore we can work out phi as a function of x, and then you end up with phi function of x equals to 8 minus 2x, where x is in meter. So going back to our graph, okay, so we can plot the potential, and that will be equals to 8 minus 2x. And then the surface where you have a constant phi. So if you substitute x equals to 1, you get phi 1 equals to 6, phi 2, 4, 2, and then phi 4 equals to 0. Okay, so that is your x equals to 1. This will be your constant Okay, so that is the example. Okay, so that is for uniform electric field. So if it's non-uniform, then the electric field changes with the distance x. Then we end up with this equation here. Okay, so instead of just doing a constant gradient, then the electric field becomes minus d phi over dx. Okay, this is for one dimension, just changes in the x direction. So the magnitude of the electric field is a negative gradient of the potential. The direction of the electric field is in the direction in which the potential is decreasing. And that's the meaning of the minus sign in equation 8. Okay, it's a decreasing potential. So if you ask to find the electric field, so we first find the potential, then we can find the electric field using equation 8. Because potential is a scalar. Okay, so you can calculate the potential, and then you can use equation 8 to work out the electric field. Okay, just now equation 8 is one dimension, just x direction. So if it changes in 3 dimensions, x, y, and z, then we can extend the equations. So the electric field will be 3 different components, Ex, Ey, and Ez. And then you can do partial differentiation with the direction x, y, and z. And that leads to these equations here, which is the gradients of the potential. Okay, so in vector calculus, the electric field E will be equals to minus gradient of the electric potential, or gradient of the potential. Okay, remember our operator, our del operator, which is a vector operator of d, or del over del x, del over del y in the y direction, del over del z in the z directions. Okay, so we have equations 9b, 9c, they are all referring to the same thing. Okay, 9a here. Okay, so they are all, so 9a is in terms of individual components, E equals to E of x, E of y, E of z, and then break it down into the individual components. Or 9b, E equals to minus grad of phi, or 9c written in a coordinate system. Okay, so they're all referring to the same thing. It's just that different presentations. So pick your choose which one you are comfortable with. Okay, because they are all the same equations. Okay, so they all state that the electric field is minus the gradient of the electric potential and is in the direction of decreasing potential. So I can see that in this case here is the grade of the electric potential. The potential is a scalar field. And doing the grade functions, we end up with a vector, which is the electric field, which is a vector field. Okay, we have looked at this earlier on about converting a scalar field into a vector field by doing a gradient function, a grade function. Okay, this is the example of that. Another example to illustrate this electric field equals to minus gradients of the electric potential. So we go back to our very simple example of a point charge and see how we can get from that back to a Coulomb's law of a point charge. So the potential of a point charge, okay, can be written as Q over 4 pi epsilon naught R. So we have derived this early on, the electric potential of a point charge. So I have a point charge Q, a distance R. We can work out the potential of this, which is equals to Q over 4 pi epsilon naught R. Okay. In a 3D coordinate system, R will be a point X, Y, and Z. And therefore, we can work out our R using Pythagoras. R will be equal to square root of x squared plus y squared plus z squared. And therefore, we can rewrite our electric potential will be equal to Q over 4 pi epsilon naught square root x squared plus y squared plus z squared. Okay, so basically just getting from here to here by substituting R as square root of x squared, y squared plus z squared. Follow so far? Okay, nothing new. Electric potential. Okay, substituting R with the distance of x, y, and z in x, y, and z coordinate systems. And then we have a potential Q over 4 pi epsilon naught square root x squared plus y squared plus z squared. Okay, then we can do partial derivative for each individual components of the electric field. E of x, we're basically doing partial derivative with respect to x of that potential. Okay, so partial derivative means that we treat y and z as a constant. Okay, do you know how to differentiate this? Okay, so we assume y and z as a constant. So you can think of you integrating of let's say plus 4 is a constant. So I can think of that my y squared plus z squared as a 4, which is just a constant. Okay, so if you do that, this will be 2x times half, because I got a square root, divided by 3 over 2. Okay, so this simply equals to x over x squared plus 4, 3 over 2. So in this case here, this will be equals to x over x squared plus y squared plus z squared, 3 over 2. If I have a constant a, and then I just have a there. Okay, my a will be this slot here. Okay, so I end up with this. Okay, so x squared plus y squared plus z squared, 3 over 2, that is equals to square root of x squared plus y squared plus z squared cube. Yep, same thing. Correct? Agree, everyone? This is R, so this is R cube. Okay, so my electric field should have a negative, no, positive, negative here. Yep, because it's 1 over square root. Okay, so that is minus 1 over 2. So my x component of the electric field will be Q times x over 4 pi epsilon naught r cubed. To work out the y components, do the same, but differentiate or partial differentiate with respect to y. Intuitively, without even solving, you should guess that this is equals to q y over 4 pi epsilon naught r cubed. And that's my E of z should be q. Anyone? Z over 4 pi epsilon naught r cubed. Okay, so we have our 3 different components. Our E simply equals to EX, EY, EZ. Okay, so if you put everything back in, so this will be equals to Q over 4 pi epsilon naught r cubed x, y, and z. Alright? So my x is this Q x over 4 pi epsilon naught r cubed. My y, EY, is Q, okay, Q times y over 4 pi epsilon naught r cubed. And then my z, E of z, will be Q times z over 4 pi epsilon naught r cubed. And this is Q over 4 pi epsilon naught r squared x, y, z over r. And this is our unit vector r. And that backs to our electric field of a point charge from Coulomb's law. Okay, so we start from the potential of a point charge, do a gradient of that, or negative gradient of that. We get back our electric field, which is the same as what we have derived from Coulomb's law very early on. Okay, so when we studied Coulomb's law, we said that the electric field is equals to, for point charge, Q over 4 pi epsilon naught r squared unit vector r. Okay, unit vector r is equals to x, y, z over square root of x squared plus y squared plus z squared. And that is, and this is simply equals to magnitude of r. Okay, this. Okay, so this is just basically what I have just discussed just now. Okay, so you can get back to your Coulomb's law by doing that partial derivative of the component. Okay, I'll give you 5 minutes break, and then we'll come back to look at equipotential surface and their relationship with the electric field. Okay, equipotential surface and their relations to the electric field. So equipotential surface are those surfaces on which the potential is constant at every point. Okay, important facts. The electric field at any point is always perpendicular to the equipotential surface on which this point sits, and is in the direction of decreasing potential. Okay, so if you remember our point charge Q, we have our electric field of Q pointing away. Okay, if you calculate the electric field at a distance r, that electric field is the same. Okay, so that line there will be an equipotential line of electric field. Okay, so and then just now we calculate potential. So at infinity we set the potential to be 0, and then we bring a charge from infinity to a point r. So that charge going to the potential, electric potential, will be 0 at infinity and start increasing towards the point r. Okay, meaning that if you go from this point to infinity, the potential is going to decrease. Okay, so it's in the decreasing direction. And we know that our electric field of our point charge, if it's a positive charge, the electric field is pointing in the decreasing directions. Okay, and is also perpendicular to the equipotential surface. So this is all the points that pointed out here. So the electric field is perpendicular to the equipotential surface and is pointing at the decreasing directions or decreasing potential. Okay, so that's the physical meaning of the equation. E equals to minus gradient of the potential. So 2 points. The electric field is perpendicular to the equipotential surface and is pointing in the decreasing directions of the potential. And that is the negative signs, what the negative signs there for. To further illustrate this, okay, equipotential, another application of equipotential, we use this in the electric field to find equipotential surface, but in the map, okay, I'm not sure whether you can see this map here. Okay, so you can see here is 200 meter, here is 100 meter. So if you look at the map, there is contour around the map. So what this line here tells you, that all this contour here will be a height of 200 meters of the hill. Okay, so this is a hill. Okay, so this line here tells you that along all this part here, they are all of the same height of 200 meters from ground level, and here is all 100 meters. Okay, the direction of E field at any point is along the line of steepest descent. Okay, so if you think of a hill, so the steepest descent, if I take a right angle from this point to the next quanta, that will be the steepest descent. Okay, so if you climb a hill, very seldom you're going to climb it going up like that. Okay, because it's very difficult to climb. It's the steepest. When you go hiking, you normally go like that. Okay, because here is a gentle slope compared to going on perpendicular to the contour. Okay, so if you're going not perpendicular to the contour, the slope is gentle. It's easier to climb the hill. Okay, so the place where it's perpendicular to the contour is what we call the steepest descent. Okay, so that is the toughest path to go down a hill. It's easier to go like that. Okay, and that, but it takes a long time. Okay, but the slope is more gentle in that case. So this is just to draw an analogy of what our equipotential in our electric field. Okay, so the electric field is pointing at the steepest descent, meaning that the electric field will be pointing in this direction, 90 degrees to the equipotential surface, and is pointing at the steepest descent. Okay, so that is just to illustrate the analogy with a quanta of a map. Okay, so this is the example that I've shown just now, point charge. So the potential, as you go away from the charge, the potential is going to decrease. So you got phi 1, phi 2, phi 3, and then if you go all the way to infinity, phi going to become 0. Okay, so starting from a higher potential, you're going lower and lower until 0. And the electric field always point perpendicular to the equipotential surface and is pointing in the decreasing potential. And that is the equation E equals to minus grade of phi, or gradient of the potential. So E is perpendicular to the equipotential surface everywhere in the direction of decreasing potential. And for positive charge, it acts as a source of electric field. And the potential decreases with increasing distance from the charge. Okay, in the equipotential surface, each point on the surface has the same potential. Okay, so going back to here, so all this line here, okay, all this line here, all this has a potential of phi 2. Okay, because we know that phi is equals to Q over 4 pi epsilon naught R, and all this has the same distance from the charge. So important points, every point on conductor surface is at the same potential. This is a equipotential surface on a conductor surface. If we earth the conductors, then the potential will be 0. If uncharged isolated conductor, its surface is always at zero potential also. And charged isolated conductors, its surface is at a constant but finite potential. A conducting sphere of charge Q with radius A. Okay, we have look at this. So if we have a sphere of charge Q on the surface, then it looks as if it is a point charge at the center of the sphere. And therefore, the potential of the surface is equals to Q over 4 pi epsilon naught A. Okay, so if I have a sphere, surface has a charge Q, then it is as if it is a point charge Q sitting right at the middle, and this is a radius A, therefore the potential at the surface will be equals to this equation here, Q over 4 pi epsilon naught A. Potential inside the sphere will be 0 because it's a conductor. On the surface is equals Q over 4 pi epsilon naught A. Charge build up at protrusions on conducting surface. Okay, so if I have a conducting surface that protrudes, okay, point sharper at point A, and then we'll find that practically, I mean, if you look at lightning always struck on high building or sharp points. Okay, so on buildings, trying to if you have a lightning protector in the building, normally you have a sharp iron rod sticking out of the building, and that is the protruding area where it has the highest build-up of charge in order for the lightning to discharge. So similar here, if I have a conducting surface, then the electric field has to be perpendicular to the surface. So at the top here, perpendicular, and then you have a round surface. If I draw a tangent of this, and then you have to be perpendicular to that, and so forth. Okay, so our electric field end up to look something like this, and therefore you can see that at the top, the equal potential line will be closer to each other compared to on the flat surface. And our electric field on conducting surface, that will be equals to the charge density over epsilon naught. Okay, so from this diagram you can tell that electric field is higher because it has to be perpendicular to the surface, so the electric field all squash on towards the protruding area. Therefore, based on this equation, higher electric field, which means that higher charge at the protruding area. And then here, less electric field, charge here is approximately equals to 0. No charge actually at that location, but most of the charge concentrate in this area. Okay, so the shape of an equipotential in a free space outside of the surface focus the electric field lines to the tips of the protrusions. Okay, the electric field must be perpendicular to the equipotential surface. So if I were to draw a sharp, so electric field will be and as it go lower, the electric field, so you can find that electric field here or the equipotential here is much larger as it go down, something like this. Okay, therefore higher charge. Electric field stronger here, therefore charge is also highest at the peak of this triangle. Okay, so maximum charge density and electric field at A, and then zero charge density and electric field at B and C in this diagram. So this is two equations that is important equation in electromagnetic, but we're not going to do too much details into this, but it's just to show you what they are. Okay, so in Gauss' lecture we met the differential form of Gauss' law. Okay, we write a one dimension D, or differentiates the electric flux density with respect to x in one dimension. That will be equals to the charge density in the x directions, and then we expand that into three-dimensional, and that leads to our first Maxwell equations, which is the divergence of the electric flux density equals to the charge density. And then we talk about, in this lecture, we talk about the electric field equals to minus gradient of the potential. And we know that the electric flux density is equals to epsilon r epsilon naught times the electric field. And therefore we can expand these equations into a potential, second derivative of the potential. And this is known as a Poisson's equations. Okay, so this allowed us to solve the electric field from the electric potential. And if the charge density is equal to 0, and then this equation will be equal to 0, and we have this equation 11, and this is known as the Laplace equation. Okay, so this is Laplace equation is for electrostatics potential in a charge-free region of space. And the equation 11 has a unique solutions, and therefore if you know the boundary of the problem you're solving, it has a unique solution, which means that you only have one solution. So that is important, because you can solve, knowing the boundary condition, you can solve to find out the potential of a certain surface.